Hello children, welcome to my chemistry class. I am Javashri Ghosh, teacher in Demonstration Multipurpose School, Bhubaneswar. I'm immensely pleased to have you all with me. I know children how you feel at home, but we teachers are trying our best to make you comfortable and help you in your studies. Children, today we will do the third chapter of your chemistry book, science book, that is atoms and molecules. I would like that you people be ready with your notebooks and pens when we start learning this chapter together. Okay, children, let us start. Atoms and molecules. Children, today we will be discussing development of concept of atom, laws of chemical combination, Dalton's atomic theory, limitations of Dalton's atomic theory. These are the topics we'll be discussing today. Okay? Now children, do you know the concept of atom is not a very new one. Even in ancient period, many Indian philosophers and foreign philosophers, they had given certain postulates about atoms. Some Indian philosophers like Maharshi Kannad, he postulated that if we keep on dividing the matter, and then matter was called, and now also it is called as Padarth. Okay? We will get smaller and smaller particles. And soon we will achieve the smallest particle, and it was named as Parmanu, which may not divide further. They predicted that atom is the smallest particle of a matter. Okay. Pakudha Katyama, another philosopher, he postulated that there are various forms of matter because the particles of matter exist together in combination, and that you know now also it is there. Not only the Indian philosophers but Greek philosophers like Democritus and Leucippus, they suggested that when we keep on dividing the matter, there comes a time when no more division is possible. Division of that particles. Okay, such particles they called it as atoms, which means being invisible. If we go on dividing and dividing and dividing, suppose for an example, if I take a piece of paper and I start cutting it till the last bit of paper, till mechanically we can cut it. But a time will come, we cannot do further. Okay? That part of the matter or the paper I am talking about is known as an atom. But all these ideas were not backed up by many experimental pieces of evidence until Antoine L. Lavoisier provided two laws of chemical combination. Children, you know, science is a subject which doesn't go by philosophy of facts. It needs experimentation, observation, recording and all those things. Okay, children? This Antonio Laurent de Lavoisier, he is also known as Antonio Lavoisier after the French Revolution, was a French nobleman and chemist who was central to the 18th century chemical revolution and who had a large influence on both history of chemistry and history of biology. He is widely considered in popular literature as the father of modern chemistry. Children, Antoine Lavoisier is father of modern chemistry. It is generally accepted that Some facts, we'll discuss some facts about Lavoisier. It is better to know about a scientist. It is generally accepted that Lavoisier's great accomplishments in chemistry stem largely from his changing the science from a qualitative to a quantitative one. Why qualitative to a quantitative one, children? Because then they had known about certain compounds, certain elements, but there was no facts regarding that, and that too there was no enlisting of the things, so he had done those procedures. Lavoisier is most noted for his discovery of role of oxygen, what oxygen plays in combustion. He recognized and named oxygen in 1778 and hydrogen in 1783 and opposed the phlogiston theory. What is this phlogiston theory? Let me tell you, children, before Lavoisier, people used to believe when a thing was burning or was under combustion, they believed that those combustible materials, they had something like fire inside them. Okay. Then it was believed that way. But Lavoisier, he proved the role of oxygen and he opposed phlogiston theory. There is no such fire inside the combustible substances. It is all due to oxygen. Okay. Lavoisier helped construct the metric system. The metric system one we do in our mathematics. Wrote the first extensive list of elements and helped to reform chemical nomenclature that is being used today. He predicted the existence of silicon in 1787 and was also the first to establish that sulfur was an element in 1777 rather than a compound. Before this, people used to believe that sulfur was a compound, but Lavoisier, he said no, it's an element. He discovered that although matter may change its form or shape, its mass always remains the same. Then he gave the laws of chemical combination. What is chemical combination, children? When two or more reactants, that is two or more matter, they react together and form a product, we call them chemical combination. For example, like when two compounds or elements, they react, they are known as reactants and they form a final, some matter is formed that is known as product. This is a chemical combination. Now, laws of chemical combination are, first law, let us discuss, law of conservation of mass. Mass can neither be created nor destroyed in a chemical reaction. According to the law of conservation of mass, matter can neither be created nor destroyed in a chemical reaction. It remains conserved. What does it actually mean? It means that mass of reactants will be equal to the mass of products. For this, children, as I have told you, science without demonstration, without experiment is incomplete. Now we'll perform an experiment. Let me tell you the activity first. In this activity, what we do, children? Let us take some copper sulfate solution in a conical flask and some sodium carbonate solution in an ignition tube. I'll tell you what are these. Then we hang the ignition tube in the flask by a thread. Okay. Find the mass of the flask on a balance, using a balance. Then we tilt the ignition tube and reaction takes place and sodium sulfate and copper carbonate are formed. Then we find the mass of the flask. It will be seen that the sum of the masses of the reactants will be equal to the mass of the products. Okay. Now see in this experimental setup. We have a weighing machine, we have conical flask, we have the ignition tube. The small test tube is known as the ignition tube. law of conservation of mass disease. Okay, and when we mix that, ignition tube is dropped in the chemicals in the ignition tube are dropped in the solution. What do we get? We get sodium sulfate and copper carbonate. Copper carbonate is the precipitate formed. Children, now I am going to demonstrate one such experiment, but I have taken with different type of chemicals. Children, I am emphasizing to do this here because in class 9th you have the practical regarding this. Okay, but I know children, during this time it is not possible to have a practical class or you cannot visit the laboratory. Okay, so let me try out with one or two experiments for you. Okay children, first let me show you what I have with me. Children, I have got copper sulfate with me. Okay, and to save time, I have kept ready the solution. I take one small spatula of copper sulfate, then I add some water and I make this solution. Similarly, I have sodium carbonate. This is the sodium carbonate powder inside that, and I have made one solution of sodium carbonate just for saving my time. Okay, next, what do I do? This is a conical flask as you see in the picture. This is a conical flask. Okay, let me add some copper sulfate solution here. In this conical flask, let me add some copper sulfate solution. You see this such a bright blue color. Okay children, I have taken this much copper sulfate solution. Then with copper sulfate solution, I will be adding sodium carbonate. Not with this now, but first let me take it in the ignition tube. You see, this is the small test tube is known as the ignition tube. I am wiping it because it should not mix with the solution now. Okay, let me wipe it so that the solution doesn't get mixed with the copper sulfate solution. Solution in sodium carbonate doesn't get mixed with it now. Now just let me drop this slowly so that it doesn't get mixed. Okay children, this is what I do. Now let me weigh this. Children, the weight comes out to be 39.885. The weight comes out to be 39.885. Yes, it is constant at 39.885. Let me take it out. Okay. Now what do? I just tilt it. It's not just possible to tilt it. I'll mix this. Children, can you see this beautiful copper carbonate solution? Okay. See this beautiful copper carbonate solution. Okay. This is a precipitate formed. The product is a precipitate formed. You can see the precipitate here, children. 39 point something. 39.8. Okay. Now, here children, we have a bit difference in the weight. This is all just due to dust and air resistance and all those things. Minor variation in weight can be accommodated in experiments. Okay children. So, this goes with the agreement of law of conservation of mass. I will show you one more experiment. Children, before that, you would like to see the precipitate formed. If I show you the beautiful precipitate, I'll mix these two, that is sodium carbonate and copper sulfate solution. See the precipitate. Lovely precipitate is formed. What is that precipitate? Two insoluble liquids. These two liquids are not soluble with each other. They form layers, and this is how a precipitate is formed. See a lovely precipitate. Okay, children? Children, let us do one more experiment with another pair of chemicals. Children, I have taken lead acetate. Okay, lead acetate, I have made a solution of lead acetate just to save time. Okay, now one more solution, that is potassium iodide. I have made a solution of potassium iodide also. Let us use these two. Now let me take some lead acetate in this conical flask. Okay. What shall we form? Lead acetate plus potassium iodide. We will get lead iodide and potassium acetate as products. And children, you know, the lead iodide is a precipitate with lovely color. Let us see what color we are getting. In the last experiment, we have got a greenish blue color of copper carbonate. Light greenish and blue is maximum. Here, what do we get? This is potassium. This is lead acetate solution. This is this amount of lead acetate I have taken. Okay, in this ignition tube, let me add some potassium iodide. That is potassium iodide. Okay, see here. Now I'll drop it this way. Slowly I'm putting it so that it doesn't get mixed up. I'll wait now. Let's see what's the weight now. The weight comes out to be 39.074. Please note it down. It is 39.07. Oh, it has changed. 39.079 is the constant weight. 39.07. It's varying. Let's take it to be 39.076. Okay, final weight. It's not varying. Now, let me tilt this. Let me just drop this one. Children, can you see what type of precipitate is formed? A lovely yellow precipitate of lead iodide. You might have read in your books also, the color of this precipitate is yellow color. Okay, let me weigh it again. It comes out to be, children, 39.066. 39.066. Please note it down, children, so that you can find the variation. Children, for reactants, when we subtract this weight of reactants and products, we get very minute difference, and this difference is admissible in this type of, because there are certain environmental constants. When we do this experiment, dust is there, air resistance is there, so bit of variation is there. Okay, so that is admissible. This type of error we generally come across. So in both the experiments, what did we see? We saw that mass of reactants is equal to the mass of the products. Okay, children? And here, along with this, you had your practical portion also. Let me show you again the beautiful yellow precipitate once more. See the lovely yellow precipitate, children. This lovely yellow precipitate, insoluble. See, one solution is the two insoluble solution, lead precipitate and potassium acetate. Okay. Lead iodide is yellow precipitate. So children, we are finished with this law of conservation of mass demonstration. Let's go for the important part, and you'll be very excited to do this, I know. Children, let's solve this numerical. Based on this experiment, I have got a numerical question for you. In a reaction, 5.3 grams of sodium carbonate reacted with 6 grams of acetic acid. Okay. The products were 2.2 grams of carbon dioxide, 0.9 grams of water and 8.2 grams of sodium acetate. Show that these observations are in agreement with the law of conservation of mass. So, let's see what is the total weight of the reactants and total weight of the products. The equation is here. Sodium carbonate plus acetic acid will give rise to sodium acetate plus carbon dioxide plus water. Now see here. 5.3 grams plus 6 grams. The total comes up to be 11.3 grams. That is the LHS. What about the RHS, the product? 8.2 grams plus 2.2 grams plus 0.9 grams. Simple. You can use your notebooks and pens, children. The total weight of the products is same as 11.3 grams. So, is it in agreement with the law of conservation of mass? Yes, it is in agreement with the law of conservation of mass. Okay, children? You can solve similar examples from your book also. Now, let's do the second law of chemical combination. It is the law of constant proportion or law of definite proportion. We can call it both ways. What does this law say? This law says the elements are always present in definite proportion by mass in a chemical substance. Here it says they are present in definite proportion by mass means, children, suppose when these laws were proposed, there was no concept of atomic mass or atomic weight. They used to find the weight of atoms or the weight of elements, not atom, weights of elements or compounds by just comparing them. For example, suppose they took 9 grams of water. 9 grams of water and they could find that 1 gram of hydrogen when reacts with 8 grams of oxygen, it forms 9 grams of water. Okay. Then they found out when they experimented with 18 grams of water, they could find out that 2 grams of hydrogen and 16 grams of oxygen, they combine to form 18 grams of water. So by various experiments, they could conclude that in water, hydrogen and oxygen, they are present in the ratio 1:8 by mass. Okay. When 1 plus 8 will give you 9 grams of water. 2 plus 16 will give you 18 grams of water. Okay. So they are in the ratio 1:8. Similarly, they conducted various other experiments with carbon dioxide, carbon monoxide and all those compounds. And they concluded that a pure chemical compound contains the same elements combined together in a fixed proportion by mass and is given by the law of definite proportion. For example, if we take water from river or pond or ocean both, has oxygen and hydrogen in the same proportion. They experimented with the water from different sources and they could see that 9 grams of water contained 1 gram of hydrogen and 8 grams of oxygen. That is, they are in the ratio 1:8 by mass. Okay, children? Let's go for a numerical for this so that your concept will be quite clear. Now, hydrogen and oxygen combine in the ratio 1:8 by mass to form water. That we have discussed, children. What mass of oxygen gas would be required to react completely with 3 grams of hydrogen gas? Think, children. It's very easy. It's just simple unitary method, children. When hydrogen is 1 gram, oxygen is 8 grams by mass and we form water 9 grams. When hydrogen is 3 grams, what will be the mass of oxygen? Into 8, that is 24 grams. Simple unitary method. Okay, children? So, 3 grams of hydrogen reacts with 24 grams of oxygen to form how many grams of water? 3 plus 24, 27 grams of water. I think, children, you are clear with this? Okay. Now, let's move to another part of theory of atoms. And it was given by John Dalton, FRS. Dalton was an English chemist, physicist, and meteorologist. He is best known for introducing the atomic theory into chemistry and for his research into color blindness. He had also researched on color blindness. That is why this color blindness is also sometimes referred to as Daltonism in his honor. John Dalton was born into a Quaker family from Eaglesfield near Cockermouth in Cumberland, England. His father was a weaver. He received his early education from his father and from Quaker John Fletcher, who ran a private school in a nearby village of Partshaw Hall. Dalton's family was too poor to support him for long, and he began to earn his living from the age of 10 in the service of wealthy local Quaker Elihu Robinson. Children, I'm sharing all these things with you. It's a, you can say, sort of motivation. These great personalities who all have contributed to our education, to our subjects, what type of lifestyle they had and what they had to undergo, how they lived to come to this stage. This is an inspiration for you all, children. John Dalton proposed an atomic theory which acted as an explanation for the above two laws. Above two laws were given by Lavoisier, but it was just facts were stated. But John Dalton, what he did? He explained by certain theories. As per the theory, all matter, whether it is an element, a compound, or a mixture, consists of tiny invisible particles called atoms. So, we call it Dalton's atomic theory. Now, let's see. What are the postulates of atomic theory by John Dalton? The matter is made up of tiny particles called atoms that cannot be divided further. We have discussed that. Atoms are the teeniest particle and that cannot be divided further. First, children, let us see and learn the postulates. Then we'll come to the description of that. Atoms are neither created nor destroyed during a chemical reaction. Atoms of an element exhibit same nature. They have the same size, mass and character. Children, he also postulated atoms of different elements exhibit variant nature. They do not have same characteristics. Atoms form compounds by combining in a ratio of whole numbers. And we'll see that how. A compound contains a constant number and kind of atoms. These were the 6 postulates by John Dalton about atom. This is known as postulates of atomic theory. Now let's discuss one by one. Atom is made up of tiny particles called atoms. Matter is made up of tiny particles called atoms that cannot be divided. As I had discussed earlier, if we take a piece of paper and tear it and tear it and tear it, and we will come to a time when we cannot break it further. And that entity is known as an atom. Here also you see, children, suppose this figure is an matter. Then how it gets divided? See here. Division is possible. This is also possible. This is also possible. But the last part, this we cannot divide it further. This is indivisible particle and that's an atom. Okay. Let me tell you one thing here. Atom of a matter possesses all the characteristics of that matter. Okay. Atoms are neither created nor destroyed during a chemical reaction. Okay. Suppose we see a chemical reaction, element A reacts with element B. Then they form element AB, a compound AB. Okay. Here you see element A as a whole is present, element B is present in reactants, and in products what happened? Both all the atoms of element A and element B are there in the compound AB. Atoms of an element exhibit same nature. They have the same size, mass and character. Here suppose this is an element A and there are various atoms inside it. You can see the atoms inside it. Okay. All the atoms have same, here I have considered the color and the size. The possible things. They have the same nature also. Okay. Here in element A, you have same size of, same color of atoms. Now, atoms of different elements exhibit variant nature. They do not have same characteristics. You can see, children, in element A, you have different types of, lots of atoms, okay, and their shape and size are equal. In element B, you have lots of atoms whose shape and size are equal. But what happens? Is all the atoms of element A is similar with all the atoms of element B? No, they vary. Okay, different elements have different types of atoms and they vary in their characteristics also. Here you see they are blue and little bigger atoms. Here you see they are green and little smaller. This is just for demonstration purpose. Okay, children? Now, atoms form compounds by combining in a ratio of whole numbers. We have known, children, H2O is water in whole numbers. Okay, 2 atoms of hydrogen combines with 1 atom of oxygen to give H2O. Similarly, one atom, you can see in the screen, 1 atom of carbon combines with 2 atoms of oxygen to give carbon dioxide. And carbon dioxide in any form from anywhere will have this combination only. And they combine in whole numbers, H2O2 hydrogen peroxide. Okay. MgO, NH4Cl, all these are combining in the ratio of whole numbers. Okay, we never find H 2.3O or C 5.4O. We don't find these type of combinations. Actually, they combine in a ratio of whole numbers. Children, a compound contains a constant number of kind of atoms. Okay, like I had discussed, water. Water is two atoms of hydrogen combined with one atom of oxygen to form water. Water from any source. It may be a river, it may be a well, it may be tap water, it may be sea water, it may be rainwater. But water from any source will have the combination of two atoms of hydrogen and one atom of oxygen. Okay, children? Children, Dalton has given his own theory and postulates, but there might be some limitations also. People may not agree with that. But later on there were lots of development and people disagreed with Dalton's atomic theory. But remember one thing, these are the basic postulates of chemistry, that is theory of atoms. But there are certain limitations. Let's discuss what are the limitations. It does not account for subatomic particles. Later on, after Dalton, many other scientists came and they could find out. They said that atom has some subatomic particles like electrons, protons and neutrons. Okay, children? But Dalton had not explained about that. Let me tell you one thing. Atoms of an element exhibit the same character of that particular element. For example, atoms of oxygen will show the characteristics of oxygen. Atoms of sulfur will show the characteristics of sulfur. But remember one thing. Protons, electrons and neutrons are same in all the atoms. They are the subatomic particles, we agree, but they are same in all the atoms. Okay, number might be different, but the characters are the same. Their charge and their weight are same in all the atoms. One more limitation. It does not account for isotopes. What are isotopes? You will read in later classes. Isotopes means they have isotopes of an element have different atomic masses. Atomic number is same but different atomic masses. That is, for example, in hydrogen, they have hydrogen, deuterium and tritium. But Dalton's atomic theory could not account for this. One more limitation. It does not account for isobars. What are isobars, children? Isobars means two different elements will have same atomic mass. These things were developed later on. This theory states that the mass of the atoms of two different elements must differ. But it is possible for two different elements to share the same mass number. Such atoms are called isobars. Argon 40 and calcium also has atomic mass 40. All these were discovered later on. One more thing. Elements need not combine in simple whole number ratios to form compounds. This was postulated by Dalton. But later on it was found that in some organic compounds, for example sugar, sucrose, it is C11H22O11. Like large number of carbon chains are there. One more limitation is there. This theory does not account for allotropes. The difference in the properties of diamond and graphite, both of which contain only carbon, cannot be explained by Dalton's atomic theory. Carbon is a non-metal, we know that. Carbon is soft, but diamond and graphite are the allotropes of carbon, but diamond is hard and shining, whereas carbon is not. Graphite can conduct electricity, whereas carbon cannot. Okay, children? These are the limitations of Dalton's atomic theory. Children, before coming to end, let's have the main thing of this part of discussion. These are certain assignments, home assignments for you. I know you'll be able to do it because these are discussed and are quite easy. Which postulate of Dalton's atomic theory is the result of law of conservation of mass? That you can write very well. Second, which postulate of Dalton's atomic theory can explain the law of definite proportion? That is also proposed there. Then comes a simple numerical question. A 0.24 grams of sample of compound of oxygen and boron was found by analysis to contain 0.096 grams of boron and 0.144 grams of oxygen. Calculate the percentage composition of compound by weight. What you have to do here, children? Just read the question, it's very simple. You find the percentage of boron. How do you find it? 0.096 divided by 0.24 into 100. Okay, simple. What about oxygen? 0.144 divided by 0.24 grams into 100. You find the percentage of composition of these oxygen and boron. Simple, you can do it. The fourth question is a bit tricky. When 3 grams of carbon is burnt in 8 grams of oxygen, 11 grams of carbon dioxide is produced. Okay. What mass of carbon dioxide will be formed when 3 grams of carbon is burnt in 50 grams of oxygen? Which law of chemical combination will govern your answer? You know, children, when 3 grams of carbon burns with 8 grams of oxygen, it will give carbon dioxide 11 grams. Okay, that is a fixed part, fixed composition. Here also, 3 grams of carbon burnt in 50 grams of oxygen is given. But you know, children, 3 grams of carbon can burn with only 8 grams of oxygen to give carbon dioxide. Okay. So here also it will burn with 8 grams of carbon dioxide and remaining 42 grams will remain as such. I think, children, you can do this very well. So, that's all for today. Sit down with your pen and paper, try to solve these assignments and stay home, children, stay happy and stay safe. Thank you all.